125 plus years of battery history, its use in electrical forms of communication, from before the first telegraph systems to radio available for everyone. Who is this guy? Rodney Dangerfield, American comedian. Catchphrase, "I don't get no respect." That can be said of batteries used in electrical means of communication. For 100 years, without them, what have you got? Bupkis, that's what, or something as useless as this perpetual motion machine. First of all, let's get the so-called Baghdad battery out of the way. These presumed 2,000-year-old objects were reported in the holdings of the Baghdad Museum in the 1930s. A clay jar, copper cylinder, and iron rod, plus fragments of bitumen, or tar. The question was posed as to whether this constituted parts for a chemical battery to supply current for gold electroplating. Critical examination shows no means of conducting current from the jar or for maintaining a presumed electrolyte inside. The alternative speculation is that the jars were for long-term storage of scrolls. What is almost certainly clear is that the scientific investigators of the 18th and early 19th century had no known knowledge of this prior art. People were thinking about electrical methods of signaling as early as the 1750s, but only static machines were known as sources of what we could call manufactured electric fluid. One really significant discovery came in 1745 with the realization of the capacitor, a way of storing an electric charge for a short period of time. The first suggestion of an electric telegraph in print is that published by one C.M. in the Scots Magazine of February 17, 1753. The device described would consist of running a number of insulated wires between two places, one for each letter of the alphabet. The wires were to be charged with electricity from a static generator, one at a time, according to the letter it represented. At its far end, the charged wire was to attract a tiny disc of paper marked with the corresponding letter, and so the message would be spelled. The only known indicators of the presence of these electric charges were spark discharge or electroscope schemes such as a gold leaf, pith balls, or the previously mentioned bits of paper. In 1774, there is an experimental realization of the scheme described in the 1753 article by one George Lesage. In 1787, one Mr. Lemond demonstrates signaling using a group of pithball electrometers. But because these were essentially very high voltage devices of feeble capacity, electrical leakage would dissipate the charge quickly when attempts were made to extend wires to a useful distance. And who wants to string about 35 wires? (1800) Alessandro Volta's voltaic pile and crown of cups are the first documented devices to employ the concept of electrochemical generation of electric current. This illustration shows his voltaic pile, constructed with alternating disc of copper, cloth soaked with brine, and zinc. When stacked high enough, small sparks could be seen, a tingle felt, and most importantly, others observed that bubbles were liberated when connecting wires were in contact. The Achilles heel of the voltaic pile, polarization and quick drying of the brine. Internal resistance soars after short periods of operation due to the formation of gas on the electrodes, and metals corrode fast due to local current action. For the next 25 plus years, the battery is not doing anything to help us communicate in a practical way, but it is an essential tool allowing chemists to discover new elements and how to electroplate metals. It was 20 years before the Dane, Ørsted, became the first, in 1820, to link the electric force to magnetism. The caption reads, "Ørsted holds a wire above a magnetic needle supported on a pivot. The needle is deflected when electric current flows through the wire." From 1820, Ørsted, Schweiger, Ampere, and others put the electromagnet to work as an indicator of electric current in various forms of the galvanometer. Models of various electromagnetic instruments created by Schweiger, Puggendorf, and Cumming in 1821 made for an exhibit at the Museum of History and Technology of the Smithsonian Institution. From 1831, Joseph Henry in New York is making electromagnets with fields strong enough to attract or hold heavy weights, soon observes that his electromagnet can pull the iron clapper to ring a bell. That's signaling with electromagnets. Back to polarization. The voltaic pile, as soon as it starts delivering current, liberates hydrogen gas that forms bubbles collecting on the surface of the metal and thus begins to insulate the surface. How do you get around that? Cruikshank builds a trough battery that helps by increasing the surface area of electrodes and provides a container for liquid electrolyte so that it does not dry out. Amalgamation of the zinc plates with mercury is a major improvement that prevents local corrosive action with impurities in the zinc. Wollaston pours pure sand between the plates and saturates it with dilute sulfuric acid, circa 1826. These improvements power many experimental investigations in chemistry. Henry's electromagnet investigations require much more current for experiments. He invents his intensity battery, one of the most powerful trough-style batteries ever made. I estimate that the base is about 5 feet square and has 48 cells. At one point, his lab was said to have a battery of 2,000 cells, but no description of their physical size or chemistry. 1836. Englishman John Frederick Daniell, having built on the observations of Becquerel and others, tried to figure out chemical ways to depolarize batteries. The solution seemed to require two electrolytes that could not be allowed to mix but still allow current flow. The first separator for the electrolytes discovered was animal bladder, then certain varieties of thin wood. The most practical barrier found by Daniell turned out to be thin plots of unglazed earthenware. This pot sat inside a copper can. Finally, a cell soon proven to be one of the two best available batteries for our electromagnetic telegraphy systems. Time to ask, what powered the first electric telegraph to be placed into commercial service? 1837 in England, William Cooke and Charles Wheatstone enter a partnership to promote the electric telegraph commercially, a system using multiple galvanometers. They obtained permission to build a demonstration line for the London and Birmingham Railway. The first C&W telegraph line, using 5 conductors, installed in wood conduit covered with tar, installed along railway right-of-way from London's Euston Station to Camden Town, a distance of 13 miles. I couldn't pass up the opportunity to show this picture. Euston Station, London, 1837, showing wrought iron roof. A little bit of background as to why the telegraph became linked to the railroads. Mid-1830s to mid-1840s, UK railroad expansion was underway at a breakneck rate, with millions flooding in from speculative investors. The investment bubble collapsed about 1845, with huge fortunes being wiped out and fueling a depression. But Cooke and Wheatstone and others saw the telegraph as a wonderful way to manage scheduling along the tracks. The first articles about the electric telegraph are already not wasting time on talking about the batteries used. This drawing seems to illustrate for the first time what type of battery was used in Cooke and Wheatstone's first experiments in 1837. However, these instruments were not used in the first public demonstrations. This 5-needle galvanometer is identified as the first instrument to identify the letters of the alphabet. The permutating keyboard was used to deflect any 2 needles plus or minus to point to a particular letter. In this case, the leftmost and the second from right needle have points that converge on the letter V. So the displayed message could be read by anyone, but a skilled operator would be required to operate the key combinations to point to a desired letter. Charles Wheatstone, at his rooms in King's College, worked with John Daniell in 1837. It only takes about 15 milliamperes to deflect each needle, a trivial current for John's cells. But this drawing strongly suggests that Daniell's cells are being used. The 6th wire coming from the permutating keyboard is a ground return connection. This drawing matches the description of the instruments used in the formal demonstrations made to railway staff Wednesday, the 6th of September, 1837, using the 5-wire conduit line. Wall-mount Hatchment indicators replaced the original 4-needle instruments used in testing. Unfortunately, this illustration does not tell us anything about the battery in use at the time, but it was most likely a Daniell cell setup. The Great Western Railway, 1839. The first permanent line of electric telegraph in England was completed on July 9, 1839, between the Paddington and West Drayton stations of the Great Western Railway, the London Paddington Station to Bristol line, a distance of 13 miles, having taken a year to build and costing the railway £2,817. 4-needle indicators were used. Relays were not used in these needle systems for messaging. However, they devised a low-current magnetic solenoid to release a clockwork-driven escapement, causing the striking of a bell alarum to tell you a message was about to be sent. This was accomplished through an earth return circuit. Therefore, in early British telegraphy systems, batteries only had to deliver currents well under 50 milliamperes. The drawing of these instruments, presumably in service before 1843, clearly show trough batteries. They are said to have been serviceable for 2 to 5 months, as long as checks were made to add enough dilute sulfuric acid to keep the sand in the cells damp. There were 12 to 60 cells per battery, depending on circuit length. For a system requiring such low currents, the trough battery could provide a higher working voltage to compensate for line resistance at a much lower cost than to fabricate an equivalent number of Daniell cells. At left, an announcement for the first availability of electric telegraph for public messaging, predating the messaging service provided by Samuel Morse by almost a year. Previous usage only for railway control and management. On the right, this 1845 advertisement proclaims at the bottom, "By its powerful agency, murderers have been apprehended, as in the late case of Tolwell, thieves detected, and lastly, which is of no little importance, the timely assistance of medical aid has been procured in cases which otherwise would have proved fatal." In the USA, Samuel F.B. Morse and his tech guy, Alfred Vail, will take a different approach. In 1838, Morse and Vail demonstrate a telegraph using an electromagnet and code consisting of combinations of long and short marks recorded upon a paper tape at the receiving end. This was at the Speedwell Iron Works, Morris County, New Jersey. It does not make it into commercial service until 1844. They used a Grove cell, like this 1839 version, a zinc anode in a dilute sulfuric acid, and separated by a porous cup from a platinum cathode in concentrated nitric acid. It made poisonous fumes, but it could easily deliver substantial current to the electromagnet at about 1.9 volts per cell. This first 30-mile line from Washington to Baltimore is said to be the only line financed by a grant from the U.S. Congress. All others were financed by private capital. An old reference said American telegraph circuits were very poor compared to English and continental practices, suffering from high and variable leakage as well as vandalism. Instead of improving the circuit, one simply piled on more batteries. It was not unusual to use 50 Grove jars on a long circuit. The usual ratio was 1 Grove cell per 20 miles of relay line. Local circuits had separate batteries. 50 jars could supply an 800-mile relay circuit or a 50-mile register circuit. Half of the line batteries were placed at one terminus and the other half at the other terminus to facilitate the finding of line breaks and shorts. As traffic increased in the 1850s, the noxious gases emitted by these cells became a real problem. For electromagnetic telegraph systems, the use of a line relay was a crucial development. This sensitive relay could operate with the resistance in long lines and switch a heavier current to activate the magnets of a register or sounder. The practical relay was discovered by Joseph Henry in 1835, but he made no patent claims. With closed circuit operation, intermediate stations needed only local batteries, usually 1 jar of Grove or 2 jars of Daniell cells, or later gravity cells. As often happens, Research in various forms of electric telegraphy were showing up in a surprising number of countries in the 1830s and 1840s. It was a time of almost inevitable convergence in technologies that would enable working systems to be developed more or less independently, powered by Daniell, Grove, or trough cells. Bain in the USA has a chemical telegraph in operation in the mid-1840s. Schemes of printing telegraphs come online into the 1850s. Patent challenges abound in the courts here and abroad. In 1852, the first fire alarm telegraph system is in operation in Boston. By 1890, 500 cities have such systems in operation. An online reference says that in 1855, gravity cells were used, but that must be too soon for a gravity cell. It's most likely that Daniell cells were used at the start. The 1854-1855 war in Crimea marks the first military field use of the electric telegraph. This was not, however, used for tactical purposes, but merely for intercommunications between the principal headquarters of the Allied besiegers, probably more a matter of convenience than necessity. The systems used batteries described as modifications of Daniell's for the most critical circuits and trough batteries for others. Gutta-percha insulated cables were plowed into the ground, ideally about a foot deep, all using 1 or 2 needle English-built telegraph instruments. Here is a list of batteries described in the 1852 rudimentary treatise on galvanism, but most don't get used to any extent in communications. This list only goes back to 1832. There had already been 3 decades of investigations. Named are Daniell's constant battery, Grove's nitric acid battery, Smee's battery, Kemp's pile, Kemp's amalgam pile, Bunsen's battery, and on and on. All these batteries, regardless of their practical utility, at least provided documentation of a very large percentage of metals, electrolytes, dielectrics, and conductors that could possibly be used for battery construction. And now we come to the 8th wonder of the world, the Atlantic Cable. The laying of the first Atlantic cable in 1858 was a big event, even in the minds of ordinary people. The sheer audacity of investors coming together to finance the undertaking only 5 years after the laying of a 27-mile fragile cable under the English Channel required great leaps in cable fabrication technology and devising ways to transport and pay out up to 1,200 miles of cable from each of 2 ships to depths of more than 2 miles. It is an epic tale well told in several modern books. The 1858 Atlantic cable was laid and tested along the way aboard the Niagara and Agamemnon using a Thomson reflecting galvanometer and up to 75 Daniell cells, or about 80 volts. On landing the ends, the chief electrician, Wildman Whitehouse, tried to use up to 360 cells with an induction coil to kick the signal through with enough voltage, estimated to peak at about 2,000 volts, to activate his own patented recording register. The results were so poor as to be regarded as a complete failure and reverted to the galvanometer Daniell cell circuit. Sawdust was added to the electrolytes to minimize sloshing of the cells at sea, leading to a variant by Thomson and Jenkins of a tray cell, called an improved sawdust Daniell. The cable gave fitful service and failed completely in less than a month. Post-mortem investigations blamed the high-voltage testing as the primary cause for failure of the cable. But governments, military, and commercial interests could not ignore the enormous potential of instantaneous intercontinental communications. The same corporate interest mounted a second attempt to link the Old and New Worlds in 1865, with success achieved in completing 2 cables the following year. I cannot resist showing you this wonderful painting by Robert Dudley, artist to the 1866 expedition, showing the test room on board the Great Eastern. In use is the Thomson reflecting galvanometer powered by Daniell cells. The American Civil War, 1861 to 1865. By this time, commercial telegraph networks had spread extensively in northern states and to a much lesser degree in southern states. What powered Civil War field telegraph systems? This may be one of the only photographs to answer that question, but it is dated 1864. I think the error points to the copper cylinder of a Daniell cell. One narrative says that there were 96 gallon-sized cells in groups of 6. The fragile, unglazed earthenware porous pots were by necessity replaced with pots made of leather. Maybe not so good, but these cells could at least survive transport. But this could not have been the first field outfits placed into service by the Army of the Potomac on May 24, 1862. They used the Beardsley magneto-electric indicating dial telegraph machines. The dial telegraph concept had been in development for nearly 20 years and was certainly seductive in not requiring operators to know any code schemes, and some, like the Beardsley, did not use batteries. All desirable for military use, but in practice these machines were slow, difficult to keep in adjustment, or work reliably on even short loops. They were removed from service before the end of 1863. A Frenchman, M. Collode, invents the gravity cell sometime before mid-1861. Vague references that he may have reinvented a cell attributed to Cromwell Varley circa 1855 have not been proven. From the 1870s onward, the construction of the battery had morphed into the so-called crow's foot battery because of the shape of its cast zinc cathode. Gravity cells are said to last 4 to 6 months in local circuits, mainline circuits about 8 weeks, and in quadruplex circuits 5 to 8 months. For best operation, the cells must be above about 65 degrees Fahrenheit. The output is seriously affected by temperatures below 50 degrees Fahrenheit. They cannot be subjected to vibration from machinery, must remain under load but not overloaded, or the electrolytes will mix and the voltage will drop to useless values. But for 30-plus years, they were the preferred battery for telegraphy. Above, this appears to show 2 local circuit cells covered in zinc salts, with a spare jar to the left. This is with reference to useful life being 4 to 6 months. Below is a small office with shelving holding a collection of mainline gravity cells. My guess This picture dates from about 1890-1900. In 1866, George Leclanche patents a carbon-zinc battery for open-circuit use. Improvements by 1876 bring it into wide use for signaling and then rapidly adopted for telephone use in the early 1880s. One advantage being their ability to deliver useful current at temperatures well below that of the gravity cell. Here you see the first really successful National Bell Telephone Company subscriber outfit of 1879 using the Leclanche patent cell. And in just 3 years, all of the components are integrated on a single panel with the wet cell in the box at the bottom. Carl Gassner patented the first dry cell in 1887, with zinc as the container for the other elements, as well as being the negative electrode. The electrolyte was absorbed in a porous material. A depolarizer mix was packed around a central carbon electrode, and the cell was sealed with bitumen across the top. This cell was easy to handle and portable. It became the prototype for the dry battery industry. By 1889, F.L.W. Hellesen of Denmark was selling his improved version of his dry battery to the Danish telephone company. By 1899, there were at least a half-dozen dry battery makers, including the National Carbon Company, Columbia brand, from 1896 onward, and by 1900, the largest volume producer of the type. U.S. dry cell production was said to be 2 million in 1902 and 5 million in 1905, but many issues with quality of materials because of inadequate development of science-based manufacturing control. Although the first rechargeable battery was invented by a French physicist, Gaston Palant, in 1859, it was not developed into useful forms until the early 1880s. By the mid-1890s, the basic rechargeable lead-acid battery cell had evolved to this practical configuration we still know today. Lead was cast into plates with an open grid structure. A paste consisting of various blends of litharge, red lead, and sulfuric acid are packed into the grid. After an electroforming process, the pasted plates are converted into sponge lead and peroxide of lead. The two types of plates are separated by perforated insulation panels. Usually multiple plate pairs are connected in parallel and loaded into a hard rubber or glass container. Now with this practical form, from the mid-1890s, lead-acid storage batteries provide competition for primary cells in large telegraph and telephone central battery installations. Good local steam-powered dynamos are available for economical charging even if mains power is not yet available. These battery cases appear to be about 4 feet high and the modules more than 30 feet long. That's a big battery. Automotive ignition systems provide big market to spur additional technical development. What batteries were required at the dawn of radio communications, 1900 to 1906? For receiving, not much. A few number 6 or number 4 size dry batteries, commonly used in electric lanterns, or even smaller D-size flashlight batteries, or still smaller pocket flashlight batteries, were used for coherer detectors, electrolytic detectors, carborundum detectors, buzzers to generate local RFI for adjusting detectors, and Marconi receiver installations with H.J. Round's soft vacuum detectors use 6-volt storage batteries to light the filament. Around 1909, the Edison storage battery company perfected a nickel-iron storage battery, very rugged and long-lived, but high initial cost. It found a niche in railroad signaling, miners' lights, and traction batteries. It was marketed for radio usage about 1920, but not successfully. An interesting collectible is the Edison battery oil jar, not for squeaky batteries, but poured on top of the cell electrolyte to reduce evaporation. Storage batteries provide backup to run some shipboard spark transmitters. The Titanic Marconi lead-acid battery installation, brand name Chloride Accumulator by Exide, ran their emergency backup transmitter only. It was not used on the night of the sinking. Land-based rock crusher spark transmitters needed much more power, practical only from steam or mains-powered dynamos, but some have battery installation for emergency backup transmitters as well, almost all of the lead-acid battery variety. In large industrial cities in the 1908 to 1912 period, there were boys' clubs with dozens of members making their own wireless outfits. A series parallel connection of number 6 dry cells could power this $5 1-inch spark coil. Note that there is no tuned circuit for the spark coil. One side of the gap is connected directly to a 6-wire flat-top antenna. The range is usually no more than 2 miles. Detectors mentioned are the silicon or microphonic, i.e. carbon, detector variety. The DeForest RJ4 Audion detector box uses a string of pocket flashlight batteries that were on the market from before 1911, soldered together for a maximum B+ of 40 volts. External battery of either dry cells or a small storage battery provides 4 to 6 volts to light the filament. This is the only photograph I have ever seen showing the original arrangement of B batteries. The Great War brings the necessity for unitized high-voltage batteries for vacuum tube transmitters and receivers. A 22.5-volt battery is specified by the Signal Corps for receiver circuits, developed by C.F. Burgess Laboratories. On the left is used a type BA2 small battery weighing 1 pound, as used in aircraft outfits SCR 59 and 75. On the right, the type BA8 large battery weighing 5 pounds, another 22.5-volt battery, is installed inside this SCR 127 pack set. This equipment not deployed until 1918. Three and 4.5-volt flashlight batteries, 2 or 3 D cells wrapped in a common paper sleeve, are placed in service to power airplane intercoms and trench telephone and telegraph systems. The first battery advertisement in Radio Amateur News is in the second issue, August 1919. A storage B battery. A sheet Pyralin, which is a brand name for celluloid, case with the panels solvent bonded together. Rarely advertised in the USA, likely a British design. The first dry battery advertisement in Radio Amateur News is in the November 1919 issue. The first full-page advertisement appears the next month. These batteries were simply assemblies of existing dry cell flashlight battery designs or similar with minor changes to diameter or length, each cell with a paper sleeve or a egg crate type grid separator for insulation. Cells with tabs to allow soldering into series strings, threaded studs, fan stock clips, or rarely pigtail wires for external connections. Frequent addition of voltage taps, i.e. a 45-volt B battery would have a 22.5-volt tap. Big USA players in dry batteries were Eveready, Burgess, and Rayovac. There are a number of smaller dry battery manufacturers. One unverified article says that there were 115 makers of dry cells before 1930. Both the little guys and the big guys did private label branding and/or made cheaper battery versions. Big U.S. players in storage batteries were Exide and Willard, but with many small manufacturers because of the huge automobile battery market. I could just not resist including this 1923 photograph inside the New York City Radio Exposition of 1923. On the floor, a bank of 1.5-volt number 6 dry cells supplies about 135 volts for the plate circuits of 6 or 8 amplifiers, and some 36 tube filaments are lighted by banks of 6-volt lead-acid storage batteries. This was said to have been operated with complete success by members of the Radio Club of America, although the event organizers expressed deep concerns about the success of this demonstration. I would like to assemble a set of museum-grade replica batteries that could have been installed during the useful lifetime of early 1920s radios. First thoughts go to Burgess brand batteries because of their simple color scheme, but after over 5 years of searching, I have not found this early pre-1926 version of their number 6 size Radio A battery. The earliest combination of Eveready batteries, where the graphic can be fully documented, dates from March 1925, except for the uncommon batteries used in the 1923 Radiola II. It is reasonable, however, to think that a large percentage of radios made in 1922-23 would still be in service 3 years later. If so, this is what you would have found on store shelves to fill many of your radiolas and many other dry cell operated tube sets of the day. What color is it? For Eveready brand batteries of the early 1920s, the right answer is really hard to find because of green inks. On chipboard-based paper stocks, they are very prone to fade and color shift, largely due to residual acid content in the wood pulp paper reacting with moisture. The lower right picture shows my best guess as to the original color scheme employed. Black and white advertisement images are unreliable. They were altered to pop, so to speak, in black and white. Here are examples. 2 vintage, more or less true grayscale images are compared to widely used advertising cuts. In September 1925, the National Carbon Company, Incorporated, brings a new construction method for high-voltage batteries to market. A die-formed tablet of depolarizer mix with flat zinc and carbon electrodes stacked to eliminate separate wired connections. The technique only an advantage for large batteries. There is a 30% increase in volume efficiency and reduced labor, with lower actual watt-hour cost to the user. The storage battery specifically advertised for Radio A supply service was a big part of the market and now rank as the rarest of all 1920s battery types because of the booming business of recycling and rebuilding automobile batteries. Take your dead battery to a local garage and get 50 cents, or more if the case can be salvaged. The two color pictures show the only known surviving full-size Willard brand Radio A battery. No other full-size Radio A battery of any maker is known, and there were surely more than 500,000 batteries made. Almost all North American B batteries of the 1920s had threaded post or fan stock clips for connections. Most European manufacturers used little 1/8 inch internal diameter receptacles distributed across the top of the battery assembly. On purchase, you must remove a sealed pasteboard cover, tear off a paper flap, or puncture a cellophane sheet to make connections. Thus you were assured of having purchased a new battery. The Danish firm Edison had distribution and even manufacture in other countries. The late 1920s development of AC mains-powered home broadcast receivers led in 1930 to a new class of off-grid farm radios, spearheaded by a new type of non-rechargeable battery heavily promoted by the largest primary battery manufacturer, the National Carbon Company, Incorporated, under their Eveready brand. Using a new generation of 2-volt filament vacuum tubes, this battery could operate the radio for 1,000 to 1,200 hours, considered at the time to be 1 year of ordinary use. They made well over 500,000 of these air cell batteries from 1931 to 1940, but there are no known complete examples surviving. Only this cutaway store model and one good case bottom of the circa 1936-37 version. Why? No recoverable metals in these batteries, and the National Carbon Company had a solid patent monopoly on the zinc air technology. I took it upon myself to recreate 3 museum-grade replicas of the 1936-37 version of their A600 1,000-hour battery. Silicone rubber was used to make a mold of the case, and 3D CAD modeling was used to recreate the top assembly. Note that this version of the battery shows apparently the first use of a unified power receptacle on a North American-made disposable battery. For compatibility, fan stock clips are still provided, but they were dropped in 1938. Top left, circa 1937 air cell set. Not branded as such, but probably made by Detrola. Below, deluxe 1935 Atwater Kent Model 768 air cell radio with full set of 1936-37 replica batteries. Good for 1 year at a cost of about $17. That translates to a 2020 annual outlay of about $275. Each radio manufacturer had to submit their design and sample product to Eveready for verification that the filament circuit could not exceed 600 milliamperes loading of the battery. Accidental high current loads could flood the air-permeable carbon electrodes in seconds, rendering the battery useless. Spurred on by the first boom in automobile radios, radio manufacturers can add 6-volt lead-acid storage battery-powered vibrator power supplies to their farm radios. This appears to have taken an even bigger market share than the air cell or other dry battery market until 1938. Charge the battery with the wind in your car or the tractor. Got a Delco light plant? There are 32-volt powered sets as well. Throughout the 1930s, battery-powered radio-related hardware is used in exploration, commercial aircraft, remote radio broadcasting, etc. Magazines are full of simple radio projects to suit the limited budgets of radio amateurs and home constructors in the Depression era. Batteries are initially cheaper than AC power supplies. A great compilation of mid-1930s to early 1940s projects can be found in the 1945 book published by Popular Science magazine titled Radio for the Millions. In 1938, U.S. radio manufacturers obtained new lower drain vacuum tube technology, leading to a significant increase in the quantity of battery-powered radios for portable use. These new products require new battery packaging schemes and sizes to fit. The RMA, Radio Manufacturers Association, establishes standard battery socket patterns in 1938, which can be seen in this 1939 Burgess advertisement. Late 1939, RCA releases an even thriftier series of tubes in a much smaller 7-pin all-glass miniature envelope. Their BP-10 pocket radio is a hit, with production of 209,884 units from 1940 to the suspension of civilian radio manufacture in the spring of 1942. RCA looked to Eveready to design their Minimax number 467 67.5-volt battery. This new cell design again increases the volumetric efficiency of their old layer-built batteries by an additional 30%. Both miniature tubes and these new batteries to come in very handy when for Americans, December 8, 1941, radio goes to war again. This artist's rendering is likely of a BC 222 or BC 322 transceiver for artillery spotting. Massive quantities of batteries are required by more than 70 military communications devices, and that is just for U.S. forces. Field telephones like the EE-8 are produced in the hundreds of thousands. Industry production is outstripped by 1943, leading to suspension of radio batteries for the civilian market, later relaxed for rural markets and use in flashlights. Factories were sometimes churning out equipment with no batteries to fill them. Battery coordinator finally appointed by the War Production Board in 1943 to boost production and even open new plants. For example, the National Carbon Company, Incorporated, built and operated a plant in Charlotte, North Carolina from 1943 to 1945, Some battery assembly operations even used POW labor. The heaviest users that usually come to mind are the BC 1000 SCR 300 man-pack walkie-talkie and the SCR 536 handy-talkie. Motorola alone built 130,000 of the SCR 536 handy-talkies and 50,000 of the BC 1000 SCR 300 man-packs. Some uses may not be so obvious. The BC 221 frequency meter was supposed to be used to verify receiver and transmitter outfits of all aircraft before each takeoff. Small, fast discharge batteries powered meteorological instruments lofted by hydrogen-filled balloons. Navy DAG-1 direction finder and other models for general land operations, and the always important search for clandestine radio transmitter operations. Of course, Allied forces and Axis powers had their own implementations of such communications-related equipment, some with significantly different system design and power requirements, driven primarily at the highest government and military levels by their ideas of how hardware could be used to prosecute their warfare objectives. (1947) A new era dawns. Bell Laboratories staff create the first experimental transistor. An innovation that, in about 8 years, will radically change the form factor of batteries to power new communications devices and demand increased research into better chemistries and fabrication methods. A presentation on batteries in the transistor age will have to wait for another day. But even today, batteries don't get no respect. They're either too weak, too small, too big, too heavy, too expensive, too slow to charge, or don't last. Well, Rodney, I guess that's just the way things are.